Modeling with trigonometric functions. Solving right triangles for angles. In section 5.5, we use trigonometry on a right triangle to solve for the sides of a triangle given one side and an additional angle. Using the inverse trig functions, we can solve for the angles of a right triangle given two sides. Example 1. An airplane needs to fly an airfield located 300 miles east and 200 miles north of its current location. At what heading should the airplane fly? In other words, if we ignore air resistance or wind speed, how many degrees north of east should the airplane fly? We might begin by drawing a picture and labeling all of the known information. Drawing a triangle, we see we are looking for the angle alpha. In this triangle, the side opposite the angle alpha is 200 miles and the side adjacent is 300 miles. Since we know the values for the opposite and adjacent sides, it makes sense to use the tangent function. Tangent of alpha equals 200 divided by 3, using the inverse. Alpha equals tangent inverse of 200 divided by 3 is approximately 0.588, or equivalently about 33.7 degrees. The airplane needs to fly at a heading of 33.7 degrees north of east. Example 2. OSHA safety regulations require that the base of a ladder be placed 1 foot from the wall for every 4 feet of ladder length. Find the angle such a ladder forms with the ground. For any length of ladder, the base needs to be 1/4 of the distance the foot of the ladder is away from the wall. Equivalently, if the base is 8 feet from the wall, the ladder can be 8 feet long. Since A is the side adjacent to the angle and 4A is the hypotenuse, we use the cosine function. Cosine of theta equals A divided by 4A equals 1/4. Using the inverse, theta equals cosine inverse of 1/4, approximately 75.52 degrees. The ladder forms a 75.52 degree angle with the ground. Example 3. In a video game design, a map shows the location of other characters relative to the player who is situated at the origin in the direction they are facing. A character currently shows on the map at coordinates -3, 5. If the player rotates counterclockwise by 20 degrees, then the objects in the map will correspondingly rotate 20 degrees clockwise. Find the new coordinates of the character. To rotate the position of the character, we can imagine it as a point on a circle, and we will change the angle of the point by 20 degrees. To do so, we first need to find the radius of the circle and the original angle. Drawing a right triangle, inside the circle, we can find the radius using the Pythagorean theorem. -3 squared plus 5 squared equals r squared. R equals the square root of 9 plus 25 equals the square root of 34. To find the angle, we need to decide first if we are going to find the acute angle of the triangle, the reference angle, or if we are going to find the angle measured in standard position. While either approach will work, in this case we will do the latter, since for any point on a circle, we know x equals r cosine of theta. Using our given information, we get -3 equals square root of 34 cosine of theta. -3 divided by the square root of 34 equals cosine of theta. Theta equals cosine inverse of -3 divided by the square root of 34, approximately 120.964 degrees. While there are two angles that have this cosine value, the angle of 120.964 degrees is in the second quadrant as desired, so it is the angle we are looking for. Rotating the point clockwise by 20 degrees, the angle of the point will decrease to 100.964 degrees. We can then evaluate the coordinates of the rotated point. X equals square root of 34 cosine of 100.964 degrees, approximately -1.109. Y equals square root of 34 sine of 100.964 degrees, approximately 5.725. The coordinates of the character on the rotated map will be -1.109 and 5.725. Modeling with sinusoidal functions. Many modeling situations involve functions that are periodic. Previously, we learned that sinusoidal functions are a special type of periodic function. Problems that involve quantities that oscillate can often be modeled by a sine or cosine function. And once we create a suitable model for the problem, we can use that model to answer various questions. Example 4. The hours of daylight in Seattle oscillate from a low of 8.5 hours in January to a high of 16 hours in July. When should you plant a garden if you want to do it during a month where there are 14 hours of daylight? To model this, we first note that the hours of daylight oscillate with a period of 12 months. B equals 2 pi divided by 12 equals pi divided by 6 correspond to the horizontal stretch found by using the ratio of the original period to the new period. With a low of 8.5 and a high of 16, the midline will be halfway between these values at 16 plus 8.5 divided by 2 equals 12.25. The amplitude will be half the difference between the highest and lowest values. 16 minus 8.5 divided by 2 equals 3.75, or equivalently, the distance from the midline to the high or low value. 16 minus 12.25 equals 3.75. Letting January be t equals 0, the graph starts at the lowest value, so it can be modeled as a flipped cosine graph. Putting this together, we get a model h of t equals negative 3.7 cosine of pi divided by 6t plus 12.25. H of t is our model for hours of daylight, t months after January. To find when there will be 14 hours of daylight, we solve h of t equals 14. 14 equals negative 3.75 cosine of pi divided by 6t plus 12.25. 1.75 equals negative 3.75 cosine of pi divided by 6t. Subtracting 12.25 and dividing by negative 3.75, using the inverse, multiplying by the reciprocal, we get t equals 2.0563 multiplied by 6 divided by pi equals 3.927. T equals 3.927 months past January. There will be 14 hours of daylight 3.927 months into the year, or near the end of April. While there would be a second time in the year when there are 14 hours of daylight, since we are planting a garden, we would want to know the first solution in spring, so we do not need to find the second solution in this case. Example 6. An object is connected to the wall with a spring that has a natural length of 20 centimeters. The object is pulled back 8 centimeters past the natural length and released. The object oscillates 3 times per second. Find an equation for the horizontal position of the object, ignoring the effects of friction. How much time during each cycle is the object more than 27 centimeters from the wall? If we use the distance from the wall x as the desired output, then the object will oscillate equally on either side of the spring's natural length of 20, putting the midline of the function at 20 centimeters. If we release the object 8 centimeters past the natural length, the amplitude of the oscillation will be 8 centimeters. We are beginning at the largest value, and so this function can most easily be modeled using a cosine function. Since the object oscillates 3 times per second, it has a frequency of 3, and the period of one oscillation is 1/3 of a second. Using this, we find the horizontal compression using the ratios of the periods. 2 pi divided by 1/3 equals 6 pi. Using all this, we can build our model x of t equals 8 cosine of 6 pi t plus 20. To find when the object is 27 centimeters from the wall, we can solve x of t equals 27. 27 equals 8 cosine of 6 pi t plus 20. Isolating the cosine, using the inverse, 6 pi t equals cosine inverse of 7/8, approximately 0.505. T equals 0.505 divided by 6 pi equals 0.0268. Based on the shape of the graph, we can conclude that the object will spin the first 0.0268 seconds more than 27 centimeters from the wall. Based on the symmetry of the function, the object will spin another 0.0268 seconds more than 27 centimeters from the wall at the end of the cycle. Altogether, the object spins 0.0536 seconds each cycle at a distance greater than 27 centimeters from the wall. In some problems, we can use trigonometric functions to model behaviors more complicated than the basic sinusoidal function. Example 7. A rigid rod with length 10 centimeters is attached to a circle of radius 4 centimeters at point A, as shown here. The point B is able to freely move along the horizontal axis, driving a piston. If the wheel rotates counterclockwise at 5 revolutions per second, find the location of point B as a function of time. When will the point B be 12 centimeters from the center of the circle? To find the position of B, we can begin by finding the coordinates of point A. Since it is a point on a circle with radius 4, we can express its coordinates as 4 cosine of theta, 4 sine of theta, where theta is an angle shown. The angular velocity is 5 revolutions per second, or equivalently 10 pi radians per second. After t seconds, the wheel will rotate by theta equals 10 pi t radians. Substituting this, we can find the coordinates of A in terms of t. 4 cosine of 10 pi t, 4 sine of 10 pi t. Notice that we have the coordinates of point A. We can relate this to point B. By drawing a vertical line segment from A to the horizontal axis, we can form a right triangle. The height of the triangle is the y-coordinate of the point A, 4 sine of 10 pi t. Using the Pythagorean theorem, we can find the base length of the triangle. 4 sine of 10 pi t squared plus b squared equals 10 squared. B squared equals 100 minus 16 sine squared of 10 pi t. B equals the square root of 100 minus 16 sine squared of 10 pi t. Looking at the x-coordinate of point A, we can see that the triangle we drew is shifted to the right of the y-axis by 4 cosine of 10 pi t. Combining this offset with the length of the base of the triangle gives the x-coordinate of the point B. X of t equals 4 cosine of 10 pi t plus the square root of 100 minus 16 sine squared of 10 pi t. To solve for when the point B will be 12 centimeters from the center of the circle, we need to solve x of t equals 12. 12 equals 4 cosine of 10 pi t plus the square root of 100 minus 16 sine squared of 10 pi t. 44 minus 96 cosine of 10 pi t plus 16 multiplied by cosine squared of 10 pi t plus sine squared of 10 pi t equals 0. At this point, we can utilize the Pythagorean identity, which tells us that cosine squared of 10 pi t plus sine squared of 10 pi t equals 1. Using this identity, our equation simplifies to 44 minus 96 cosine of 10 pi t plus 16 equals 0. Combine the constants and move to the right side. Divide. Make a substitution. By symmetry, we can find a second solution. Cosine of u equals 60 divided by 96. U equals cosine inverse of 60 divided by 96, approximately 0.896. U equals 2 pi minus 0.896 equals 5.388. 10 pi t equals 0.896, so t equals 0.0285. 10 pi t equals 5.388, so t equals 0.1715. The point B will be 12 centimeters from the center of the circle, 0.0285 seconds after the process begins, 0.1715 seconds after the process begins, and every 1/5 of a second after each of those values.